So welcome back to the online Spintronics seminar series. This is our 25th seminar, and I'm happy to introduce Professor Mairbek Chshiev, whose talk will be about proximity effects in nanostructures with transition metals, insulators, and two-dimensional materials. Professor Chshiev teaches at the University of Grenoble in France, and he's also head of the theory and modeling group at Spintech. He received his PhD degree in 1997 from Lomonosov State University in Moscow, and his habilitation degree in 2008 from Joseph Fourier University, which I believe is now part of the University of Grenoble. Dr. Chshiev held several postdoctoral appointments in France and the United States between 1998 and 2004, and then worked at the Mint Center at the University of Alabama as a research scientist before finally moving back to Grenoble in 2008 when he joined Spintech. So as I said, he is now head of the theory and modeling group at Spintech, and 2 years ago he was also appointed the director of the European School on Nanosciences and Nanotechnologies. Dr. Chshiev's research is in the theory of spintronic phenomena in magnetic nanostructures, and today he will show how this theory is applied to spin orbit and magnetic proximity effects. So please welcome Professor Chshiev, and please go ahead.
Yeah. Many thanks, Kirill, for your kind invitation and introduction. And so you already announced my title, so I will do it a little bit like a cover spin orbit and, as you said, magnetic proximity effects in a variety of interfaces and structures based on transition metals, insulators, and 2D materials. And before I start, of course, I have to acknowledge and thanks my collaborators. Without them, it would be very hard. And first of all, it is Hongxing Yang, who was my first PhD student when I was in France. Came back to France, and now then postdoc, and now he is actually professor in Ningbo in China. And Ali Halal and Fatima Ibrahim, they are working with me like already 5 years, 6 years, and excellent theoreticians. Ali is now looking for a permanent position, so he's excellent, and I highly recommend him. Fatima is also applying for position. Excellent also. So Sergey was spent with me like 18 months, and now he's in Japan, Sergey Nikolaev. And Daniel Solis was my PhD student. He graduated 2 months ago, and now he's a postdoc in Paris. And my collaborators, first of all, was Professor Albert and Vincent Cross in Ceneres Tales, then my colleagues in Barcelona, Stéphane Roche, my colleague here in Grenoble, Xavier Weintal, my colleagues in Paris, as you see here, and also, again, in Grenoble Nail Institute, and my colleagues abroad. I really acknowledge them. And of course, Bernardini and all colleagues at Spintech. And on the right side, you see, this is a funding I would like to acknowledge also, of course, including European and French national agency support, and also Grenoble Nanoscience Foundation, as well as some university support as well. So let me now, I will start a little bit from historical perspective, and I'll start like from perpendicular magnetic anisotropy. So this is one of the spin orbit phenomena I think we should start from. Why it is important for spintronics, and one of the applications is a spin torque MRAM. And we know that in this application, in this MRAMs, we write parallel anti-parallel state by passing the current. And it is proportional to thermal stability factor, which is a ratio of anisotropy energy to temperature, and to Gilbert damping. But that is giving us a problem because in order to keep it low, I mean, actually, these perpendicular magnetic tunnel junctions, they have advantage because we don't have a penalty in order to pull magnetization out during the writing. But at the same time, here still, in order to have a perpendicular magnetic anisotropy, we need to use, usually, traditionally it was used many years ago, to use the heavy metals, etc. But that is increasingly dumping. And this is a classical retention versus writability dilemma. And actually the solution is to using the magnetic metal oxide interfaces as we described with my colleague, with Bernard, in this review recently. And also here what I'm showing is actually the first experimental demonstrations with a spin tech in 2002, where they started to see, my colleagues, the perpendicular magnetic anisotropy, and then this very important work by Hideo Ono's group in Japan, where they fabricated a tunnel junction, which was fully perpendicular, etc. A second way, first, it is interesting that Mihai Miron, a colleague of mine who is at SpinTech as well, he was actually using those structures in order to study domain wall motion when he suddenly discovered spin-orbit torques, as you know, and then there is a Rashba effect coming, spin hole, which are giving rise to the spin-orbit torques. And Aurélien Manchon, who is also a former PhD student, and he was one of the speakers during this seminar series, he was actually developing a theory on this, as you've heard already. And another very important thing here, again, studying these structures, the Dzyaloshinskii-Moriya interaction, which is giving rise to these topological magnetic quasi-particles, which are called skyrmions. And those are like now giving like how spin-orbitronics, all these phenomena, they are playing really a significant role today. And there is actually another approach, is what about two-dimensional materials like graphene? You put it on the top of a cobalt, and there is a strong perpendicular magnetic anisotropy. This is what I'm going to talk about. And talking about the graphene is actually, I will show you also some results about the Dzyaloshinskii-Moriya interaction. Those interfaces extremely interesting. But more generally, graphene spintronics, you can see in these reviews, is actually very, very quickly developing an emerging field of spintronics recently, and of general two-dimensional materials. And one of the areas in there is a proximity-induced phenomena. What I mean here is by making graphene magnetic by putting it on the top of a magnetic insulator, for example. And this is exactly I'm coming to an outline. I will show you some physical origins and mechanisms of a perpendicular magnetic anisotropy and DMI in metallic ferromagnet heavy metal interfaces, or magnet with the oxide interfaces, and also with the graphene. And then several recipes, how can we enhance both the PMA and DMI, how can we control them? And then there is, if I have time, I hope I will, the whole bunch of a new novel family of transport phenomena, which are called proximity magnetoresistance, proximity electroresistance, and proximity multiferroic resistance, and which are emerging also. So everything I will show you today, we use DFT combined with the tight binding approaches, and this is the code we are using. And Quant is one of the developers of it is Xavier Weintal, who is also here in a neighbor lab, and we collaborate. So let me start about the anatomy, what we call it. So what you see here is a iron MgO structures. The pure one, so is 7 monolayers of iron. On the top of it is a magnesium oxide. And then we over-oxidize it, just iron slab for comparison. We under-oxidize, or we remove an Mg. And what we did first is we actually identified what are the contributions for all these situations into perpendicular magnetic anisotropy. And for example, you can see already what is the effect of magnesium oxide on the top of iron, on the top of iron. You compare black bar and red bar, and you see that how it is getting in the first monolayer here, it is increasing by about 30%, and then very importantly, it starts to contributing quite a bit in the second monolayer, etc. You can see also how overoxidation is killing PMA. So, and then we explained also the physics of that, and it is actually quite interesting to see and visualize physical mechanism of anisotropy. But of course, experimentalists, they are interested in effective anisotropy, and if we look at the anisotropy as a function of a thickness, if we include demagnetization energy into account, then obviously, beginning from some thickness, you will put back the magnetization in plane. So, and Bernard, one of my colleagues, he said that, can we actually reduce this term, which is trying to put a magnetization in plane by inserting chromium or vanadium impurities into the ferromagnet? And this is what we did. And what I'm showing here is, by the way, is, this is just a recipe. How can we increase the effective perpendicular anisotropy, but also some historical references. And here again, how can we use this anatomy technique in order to see what this vanadium impurity will do with the PMA? So again, we have here our iron. Next to it is MgO. Here we have 2 iron per layer. So let's start replacing one of them by vanadium. Here, what is happening? We put it at the interface. We immediately harmfully affecting the PMA, and it is strongly reduced. Then we put it in a second monolayer here, away from interface. We start to restore anisotropy of the first one. And finally, when we put it at the third, etc., we will restore our PMA, interfacial PMA. So the message was overall, don't put the vanadium at the interface. You have to put it somewhere in the bulk of iron if you really want to use this recipe. And then we also look at the polarizations and also found which concentration we can go in order to this works. And actually, at one of the MMM conferences, Eric Fullerton's student, who was showing a poster, it seems that there was indication that this recipe works. And let me now just briefly mention, of course, we were looking also in other materials like Heusler alloys. Here is a full Heusler's with the MgO, and we looked again for all these cobalt, iron, aluminum, or cobalt, manganese, germanium, or manganese, silicon. This was in the framework of European project HOIMEM with our partners in Germany. And we found that actually PMA is only for good, good material. Heusler is cobalt, iron, aluminum is the only one among those which is giving you the good PMA. Let me move on. What about the controlling the anisotropy? And here is about the voltage control of magnetic anisotropy. Again, of course, there was a works, and including from Evgeny Tsimbal's group, or in Japan experimental works on VCMA. But what about using anatomy technique, what I just showed you, in order to understand the contributions into this into VCMA? And here what you see is 2 interfaces, and we identify the contributions into VCMA of 2 of them, of both interfaces, and we found about 15 femtojoule per volt per meter. And the question was, which of the monolayers of iron is contributing the most into this? And we were actually quite surprised that it is not the first interfacial one, but the second from the interface, which is very counterintuitive. Where we know that electric field should hit first the interfacial iron layer. And in order to understand this, we did now the orbital hybridization analysis of anisotropy contributions, only the part which is induced again by the applied electric field. What you see on the left side is the contribution into first monolayer. And look at the absolute value. Some contributions of hybridization between different orbitals, they are actually, well, quite large, but they are canceling. Some of them, they are canceling. And overall, the first monolayer, therefore, will not contribute much into VCMA. However, the second from the interface monolayer, even though absolute values, they are much smaller, which is logical and correct compared to the first one, they are working with the same signs, and therefore that counterintuitive result is explained this way. So then we looked also Fatima, this was a work Fatima Ibrahim was working on this, and looking at what is happening with the over-oxidized or oxygen migrated case when we put an oxygen from magnesium oxide to iron. Well, in all cases, we didn't find actually much of enhancement. However, if we look at the literature, I will show actually 2 works, which, if you look actually, there is a charge-mediated VCMA, which is giving you about maybe 100, maybe a couple of hundreds of femtojoule per volt per meter. However, there is a new class of observations where it went actually even to 10,000 of a femtojoule per volt per meter. So this is 2 of those. One is a group in Nancy, here in colleagues, they reported this better, and I'm sure that that was because of ionic migration indication, or dual oxygen might move there. Therefore, they see this 1100 femtojoule per volt per meter. Another work was Geoff Beach at MIT and his colleagues. They actually reported by this ionic migration work, it is very slow dynamics, but still they found 5,000 femtojoule per volt per meter. So what's going on and how can we model it? We decided actually to take this transition from pure to oxygen migrated case. Again, it was a very time-consuming work, but let's trace what anisotropy, how it behaves as we go from that, how we're moving this oxygen from this position to that position. And what we found is anisotropy actually has two regimes. One is actually what we call reversible regime, and another what we call irreversible regime. Why we do this? Because green line here is actually the plot of a total energy of the structure when we do this. And you see that there is a barrier to overcome, and we decided that this regime might be when it is easily returnable, and therefore, well, we call it this way. And then there was actually, with Fatima and Ali and Bernard, there was this study we published, which is establishing characteristic law of how beta behaves as a function of oxygen concentration, so number of oxygens which you could move. And we found this actually quite funny sigmoidal distribution law, which behaves, we fitted with this law. So that was about the VCMA. Now I will move to graphene, still about PMA, but what graphene can do. Here, what you see is a dependence of a perpendicular magnetic anisotropy of a cobalt slab as a function of its thickness. Well, we see a PMA, it behaves well, it goes to some value. And let's see what will happen when we put a graphene on the top of it. Well, we have a quite a good boost of anisotropy, especially for all this range of thicknesses. And then we put graphene on both sides, and there is a strong enhancement. Actually, you're doubling the boost. So what's going on here, and why graphene is actually such a strong catalyzer? Hongxin Yang was working on this when he was still here, and again, by looking at the orbital hybridizations and comparing the situations of a cobalt itself and cobalt graphene, and in particular, for example, if we look at these matrix elements over there, how they are contributing, and we can already see the differences, but a simple explanation is if we compare Siemens a partial dose, we see that when we put a graphene on the top of a cobalt, the dz square, which is easily hybridizable with a pi orbital of a graphene, of a carbon, is actually moving closer to the Fermi level. And this is how we explain it. And what you see here is also charge accumulation and depletion contour plots, and you can see how graphene is actually bonding is unformed, etc. So that is actually was an insight into why graphene is boosting the perpendicular magnetic anisotropy. And our colleagues at Neil Institute, Nicolas Rougemin, Johan Corot, and our collaborators in the United States, Gong Chen and Andreas Schmidt, they did a very nice experiment, and they actually fabricated the structures. They put created a cobalt graphene interfaces on top of iridium by intercalation, and indeed, in case of a presence of a graphene, the thickness of a cobalt where you can still observe the perpendicular areas, it is actually much larger compared when you have a cobalt only. So that was like experimental observation. And then we decided also to do, well, experimentally, these are not easy to fabricate, of course, as our colleagues told us, but still, theoretically, we can go look, why not to create these super lattices or super heterostructures, cobalt graphene repeated many times. And first we looked at the anisotropy. And here we see that both surface anisotropy and effective anisotropy, you can, of course, you can go and increase it. And what we notice is that strong anti-ferromagnetic exchange coupling between cobalt across graphene. Then what you see in this figure here, we decided actually to do nickel cobalt, and I will show that work more in detail later with the DMI. But what is interesting that in such a super lattices, you can see that again, both DMI and PMA is getting enhanced, and they are correlated. But what about this antiferromagnetic exchange? it is actually quite interesting that a group in Barcelona, in this publication, they did iron, graphene, cobalt structures, and they observed this antiferromagnetic exchange in structures with the perpendicular magnetic anisotropy, which can be used as a synthetic antiferromagnet alternative to cobalt, ruthenium, etc. So that was actually kind of a very interesting experimental work, and they did it, of course, with the theoretically. They basically found also the very similar findings. And let me move now to Dzyaloshinskii-Moriya interaction. So I'm about 20 minutes, I see, and I did. Give you the insights we've got in order to understand the origin of the Dzyaloshinskii-Moriya interaction. So hope the connection is good, because I see some message which is telling it is not very stable, but hopefully everything is fine. So
let me for a few seconds, like 10 or 15 seconds.
Yeah. So you see also this message, or?
No, I didn't. It must be on your side.
Okay.
No.
Because you don't hear me well, or?
Right now it's okay, but there were like 15 seconds where we didn't hear anything. So
yeah.
If you were saying something important, maybe repeat it.
Yeah, well, I don't know if you heard about the antiferromagnetic exchange coupling in the previous slide.
Yeah, we did.
Here I was just making a transition to Dzyaloshinskii-Moriya and what I'm going to talk about. What I will show you is publishing these works, what you see here. And here is the outline of this part on Dzyaloshinskii-Moriya interaction. Especially what I will try to convince you is to demonstrate you the so-called Fert-Levy versus Rashba mechanism of Dzyaloshinskii-Moriya interaction, what we were able to identify. So could you please, Kirill, confirm if everything is fine? Yes, it's okay. Okay, so why DMI is important? Of course, you've heard again, maybe previous speakers were talking already about the skyrmions. And this is one of the first works of observation of the skyrmions. And the Dzyaloshinskii-Moriya interaction is an antiferromagnetic exchange, which is trying to tilt your spins non-collinearly. I'm sure that you already heard about. I don't need to stop here. This is just a motivation. Another motivation is it is important, very important, to explain the, for example, Rashba-induced, current-induced domain wall motion due to Rashba effect. And also, this classical work by Andrei Théville and colleagues, they show that the Dzyaloshinskii-Moriya interaction, if you don't take it into account, you cannot explain the domain wall dynamics actually. So let me now just tell a few words about the technique, how we calculate. So this is a structure we used 3 monolayers of cobalt on the top of the three monolayers of platinum. And then what we did, we related the microscopic Dzyaloshinskii-Moriya interaction parameter, really microscopic quantum mechanical. This is what is a small d here. And then a capital D is the micromagnetic one. And we actually derive this relation. And then based on this relation, we can actually estimate microscopic parameter of a DMI and eventually micromagnetic by simply calculating the energy difference between clockwise and anti-clockwise configurations, what you see here on these images. And you can get a total one when you rotate all spins of a cobalt, or you can even get anatomy by only forcing to rotate particular layer spins. And this is actually what we call layers of DMI. Let me now show you a result. First, for total DMI for several systems. And here is a platinum cobalt. Black one is a 1 cobalt, 2 cobalt, 3 cobalt on 1 platinum. Red one is a 1, 2, 3 cobalt on 2 platinum monolayers, and blue one is 1, 2, 3 on 3 platinum monolayers. What you see very nicely is it is converging. Microscopic parameter is converging to some constant. And then, well, we compared with the other structures and compared with the literature, and we also calculated like cobalt palladium. For cobalt iridium, we found actually opposite chirality. And then for micromagnetic one, of course, it should go as a 1 over thickness. and we see it actually beginning from some 3 platinum layers. We can already very nice see that it should decrease. That is totally normal. What about this anatomy technique? And very important thing what I want you. The question what we asked, and this was actually asked by Albert Fert, Professor Fert, who was asking, is can we actually look where the spin orbit energy which is creating the DMI in a first cobalt layer is located? And we can do this. And we found that actually the DMI first is almost totally located in the first cobalt interfacial layer, but associated spin orbit energy is provided by underneath platinum layer. And then we looked also on all others. You see that even second and third from interface, they have some contributions and distribution of energy, etc. The most important result is the blue bars, this one, that, and what this observation means is actually nothing but so-called Fert-Levy mechanism of Dzyaloshinskii-Moriya interaction, which this figure is showing from the works, is that this is exactly, it is that the DMI interaction between 2 spins in this magnet, is happening across this large spin orbit coupling element, which is sitting on this. Then we actually proposed, decided to see, can we combine, if we have interfaces with the opposite chirality, can we combine them and to create like a trilayers so that when we do geometrical inverse stacking, we can enhance the DMI. And before I show you how it works, actually, here I show cobalt-iridium example, and there was some controversy discussions that there are actually about the same number of groups who are claiming that cobalt-iridium chirality should be counterclockwise, and another half is claiming that it should be clockwise. We found it clockwise, actually, and therefore we chose this example, but we can use another as well. So how it works, here what you see for bilayers, the Dzyaloshinskii-Moriya interaction, for example, cobalt-platinum is anti-clockwise. If you look at the cobalt at lead or cobalt-iridium, again, we found opposite chirality. And then when you do these trilayers, so this is a recipe. You take this opposite, and this is what you are getting. You get them indeed added. So additive effect happens. However, if you look at the values, how they are combined into the total DMI, for example, platinum, cobalt with cobalt-iridium, how it creates this value here for platinum cobalt-iridium, then it is not so trivial, actually, because sometimes there is a loss, sometimes there is enhancement, and it is not trivial business, but still it works overall, the idea. And it is interesting that the colleagues, Christos Panagopoulos and his colleagues in Singapore, they actually followed this recipe and they published this very nice work, and where they did this exactly this situation where if you take platinum, cobalt, and iridium, and you replace one of the cobalt layers with the iron, there is actually the quite large DMI happening. And they did it actually both experimentally and theoretically, and they observed nice skyrmions in this system. So what about now going to interfaces with the oxides? And the first example I show you is actually my colleague Olivier Boulle, who is also at Spintech. He was asking, can you compare actually DMI, platinum cobalt, and platinum cobalt MgO? Because he was observing the very nice skyrmions at room temperature in this structure. And we compared the values, and indeed we found that platinum cobalt MgO is actually giving you quite a significant boost. It means that cobalt MgO interface is providing you also the Dzyaloshinskii-Moriya interaction. But what is interesting, however, we know that at cobalt-platinum side, the mechanism is Fert-Levy. But on this side, it cannot be Fert-Levy because oxygen cannot provide you a large spin-orbit interaction. So it might be different mechanism, which is actually Rashba, we call. And there was works by colleagues at the States in Korea. They were actually making models where indeed Rashba, you can, from Rashba Hamiltonian, you can actually basically get a DMI. And this is what we see. But in our case, what we did, we actually looked at the band structure of this interface, and we actually calculated this Rashba parameter, and we got it actually, it's quite large. And here you see also as a function of, you can see this blue star here is really the contribution into DMI coming from cobalt, provided by cobalt MgO, and you see it is 2 milli-electron volt, which is actually quite, is already comparable with the cobalt platinum. Well, I mean, it's smaller, but still, it is giving you overall for platinum cobalt MgO quite large DMI. So let's move. What about electric field control of a DMI, voltage control DMI? And we actually calculated that. Again, here we were not the first experimentally. The group in Osaka, they already experimentally observing the DMI could be controlled by electric field. But we calculated for our structure, and we found that actually the value is comparable with the one which we have for anisotropy. Basically, it is about 30 femtojoule per volt per meter. And my colleagues, LNBR and colleagues, they actually published this work where they experimentally actually observed that indeed you can control it by DMI, as was told. Now, let me move on. And again, going to DMI I'm returning to the DMI in cobalt graphene interfaces. So this is the work we did in collaboration, again, with our colleagues in the United States, in Brazil, and Hongxing and Gongchen, Hongxing Yang and Gongchen, they were actually leading this work. And it's actually what we found is cobalt graphene interface. You have here is a function of a cobalt or nickel, and you see that you can have actually quite large values, significant values of a DMI at these interfaces. And in order to answer the question, so here what we show here again is a spin orbit energy. This is what I'm talking about. It is located right at the interface, therefore it cannot be Fert-Levy, it is a Rashba. And again, in order to identify these, we can look at the band structure, and we were able to estimate here, well, it is smaller than cobalt MgO, but still it is like, you see, 80 milli-electron volt times Armstrong. And what was nice in this collaboration, that actually experimental values and the quality of the structures were fabricated, it was very, very good. It was ultra high vacuum SPLIM technique used. And well, we were actually surprised that the values were in quite a good agreement here. And of course, we are not stopping there. And Ali, he already presented in several conferences this work, and soon we'll publish it. Is actually, of course, we're looking now what is happening with other 2D materials like hexaboron nitride. And here is actually quite interesting observation that whenever your cobalt thickness is getting larger, is actually it is with in respect to graphene, it works vice versa. While for DMI, it is much better to have a cobalt HBN for anisotropy. For anisotropy, for thin layers, is actually you have a if you want to stabilize the DMI, you have to use a thick cobalts with the HBN and not with the graphene. This is what is shown is actually here. And again, of course, the Rashba and all the beautiful physics which is coming. And also, yes, what I was talking about is about this anisotropy calculation and comparison of all these cases. You see that cobalt graphene is actually giving you larger PMA compared for large thicknesses, compared to full thicknesses, basically, compared to cobalt HBN. So that was quite interesting to see. Let me briefly mention a very recent work which were published with in collaboration with Hongxing Yang in Ningbo in Ningbo and Albert Fert and other colleagues. And so this is, can we think about DMI? You know, the DMI, why I was talking always about the interfaces, because you need universal symmetry breaking, right? So, but what about standalone van der Waals materials? So here, the idea was that if you create, in this standalone, you create a symmetry by changing the, in opposite side here, you just use two different chalcogens, then DMI for manganese selenium telluride, or MnSTE, is actually tremendously large. It was a quite large volume. Obviously, with the tellurium is much larger because tellurium is heavier. And then with the atomistic approach, Monte Carlo simulations, Jinghao Liang, postdoc, who was working with us, actually these skyrmion letters, in case of MnSTE, and also isolated skyrmions, could be, and so this is what we are predicting, that in standalone van der Waals materials, you can get it. Sorry, this is a typo. there was a FGT, because I don't have a time to show you also with the colleagues we are doing with the FGT similar work. And remaining, Kirill, could you please tell me how many minutes should I have so that I...
Don't worry about that.
Okay, okay. Then I will not hurry. I will show you about the proximity-induced magnetism. So what is the idea again? We put a graphene on the top of europium oxide, for example, which is magnetic insulator. And there was actually a long time ago the work by Arne Bratas and colleagues, where they proposed actually the similar idea, and they were talking that in this system you can actually get 5 millielectron volt. We did actually first principle calculations of those, and we found actually that exchange, first of all, you see the Dirac cone. Well, it is doped, it is electron doped, but you're actually splitting Dirac cone and you're inducing quite large exchange splitted gaps. And exchange, the values is 36 millielectron volt, which is actually much larger than that earlier suggestions. And we did even the estimation of Fermi velocities based on this based on these parameters, and actually this is a very, it was like a prediction of that you can make magnetic graphene and you can induce this strong exchange within by putting it in proximity with the magnetic insulator. And then, of course, europium oxide and europium sulfide is Curie temperature is quite low. We are interested in high Curie temperature materials, and one of the most popular materials is cobalt ferrite, for example, which is used, for example, for classical spin filtering, tunnel junctions, etc. What about putting graphene on top of it? Or especially yttrium iron garnet, which is very popular material, especially for because it is low damping, etc. You know that there's a tremendous amount of activities, and we put a graphene on top of it, and in order to see whether we can actually get also similar exchange splitting induced in this. And it was extremely heavy. You see the structures are quite horrible. It took us like a year and a half only to relax this structure. It was a very, very tough work by Hongxing and Ali and Fatima. And finally we got actually, and the most interesting case is here is yttrium garnet. You see actually you have a quite nice exchange splitted gap induced over there. And if we look at the literature, both on the theory side, the values what we're getting, actually, we got actually quite larger, about 100 millielectron volt exchange. It is huge. But if we look also other works which are both exist on theoretically, there was actually other proposals in order to induce this proximity induced magnetism with graphene by different materials. But what about experiments? Or for example, Bart van Wees' group, he was already doing this Hanle precession technique in order to see and to detect this proximity-induced exchange splitting, and he found about 0.2 Tesla first, but now later they started to get larger values. And also there were some other works, including by Jagadesh Modera and colleagues, for example, they found actually quite large values. So again, this is a very, very active field now. And I don't talk here about the spin orbit, almost nothing, but there is now a huge spin orbit proximity-induced phenomenon. My colleagues in the Graphene Flagship Consortium, Stéphane Roche and Yaroslav Fabien, there is a tremendous amount of activities happening over there. But what about these four materials? The idea is can we explore now the transport in the graphene in a situation where we can induce magnetism in it? And we fitted, and this was Daniel Solis, my PhD student, this was the topic of his PhD thesis. We actually, the idea was to fit with a tight binding Hamiltonian or to first principle band structure, which is shown here with the dots. And he got this fitted done for all situations, including EGA, which is interesting, CF4. And then the idea is, so here in Hamiltonian, you recognize the hopping, exchange, and staggered potential. And then we calculate and propose a concept of such a device. So you see a lead attached to the graphene here, and on the top of it, you put two insulating magnetic insulators, M1 and M2. The idea is you get you induce magnetism only there, and when the electron is going under this magnet, is getting polarized, and then by again tuning parallel and anti-parallel configuration of these magnetizations, you can actually get what we called proximity magnetoresistance effect. And we used a very pessimistic definition, and even with this very pessimistic definition, you see we've got, actually for some cases, we've got up to 100% ideal proximity magnetoresistance ratio. In case of IG, we've got, as you see, like 75, 75, up to 80%. All the approach was done with the quant, again, in collaboration with Chshiev and Tal, and there is a Landauer formalism in order to calculate the conductance there. And so what is interesting also, I don't show it here, but the phenomena seems to be quite robust if you change the nature of the graphene edges here. You can use an armchair or zigzag or even mixed, and it is actually surviving quite well, this proximity magnetoresistance. What about additional degree of freedom? This is Fatima Ibrahim. She was working and did excellent job on this. So what the idea was, can we control this proximity-induced magnetism graphene within graphene by putting it on the top of bismuth ferrite, which is a known multiferroic material. And well, we put what we call graphene on a head side and also on a tail side. And we've got it indeed. You see that Dirac cones got splitted on two graphenes, and depending on how the polarization is looking, you can see that indeed this ferroelectric polarization seems to affect the exchange splitting values. It can affect actually the nature of the splitting. And we did it even with the spin orbit, actually these crossings, when you put a spin orbit, to estimate the Rashba strength. And we got these tight binding parameters again. And next idea is, can we explore now the transport? And this we did actually in collaboration with the Evgeny Tsimbal from Nebraska, a colleague of Kirill. And here what we've got. So the idea is the following. If you now have a ferroelectric polarizations, in addition to magnetizations, and now you have these 8 possible configurations. And based on those configurations, you can actually introduce proximity electroresistance, proximity magnetoresistance, and proximity multiferroic resistance, what we call. And here, why we talk about this, because if you look at the conductances for all these 8 configurations, you see that we have a 6 distinct, 2 of them are degenerated, but we have 6 distinct cases of conductances. It means that all those phenomena, they exist. And indeed, what is shown here is every of these phenomena, again, for all situations, and you can see that it can be both positive, negative, all of them. And well, for proximity multiferroic resistance, it is positive, but magnetoresistance and proximity electroresistance in this kind of a structure, what we call a multi-resistive concept for a device, the values are actually quite promising. And this is it. I think that I took my time, 45 minutes. This is a summary, just I hope that I showed you some insights into perpendicular magnetic anisotropy mechanism, and also Dzyaloshinskii-Moriya, especially distinction clear between Rashba and Fert-Levy stories. And also, well, what we call graphene spin-orbitronics, because the graphene seems to be excellent booster of the PMA, and good also for DMI. And now for also for proximity induced exchange, you can actually think about the transfer phenomena there. And again, I would like to acknowledge my colleagues, as I did it in the beginning, because yes, it is very important, and I really thank them for this excellent collaboration and works. And I acknowledge, first of all, is a graphene flagship. It is a big European flagship project, which is an excellent consortium of the leading labs of Europe working on this. And also I acknowledge ERC of Bernard, also this European, French, German project, and also several projects we have on a national side, and also at the Grenoble level, Grenoble Nanoscience Foundation, because Hongxing was supported initially, and even myself by that, I acknowledge support, and also Emergence Stratégique program of Université Grenoble Lab, who is supporting Sergei Nikolaev. And at that, I will put my summary slide, and I would like to thank you for your attention, and please ask the questions here.
Thank you very much, Mair, for this nice talk. So we can now take questions. To ask a question, please use the raise hand feature in Zoom. So it's under the participants panel. So find the raise hand button and
Yes.
wait for me to call upon you. If you have a question, don't wait for the previous question to be answered. Just raise your hand and we'll get to you in turn. So first question, Ghulam Morshid, please go ahead.
Hi.
Hello.
So my name is Ghulam Morshid. I'm a second-year PhD student at University of Virginia. So I have a couple of questions regarding the DFT calculation.
Mm-hmm.
So in the DMI calculation, like you showed the spin orbit coupling energy change in the metal layer. So in the structure, like you have 4 different atoms in the layer adjacent, right? So when you are showing the spin orbit coupling energy, like did you calculate
Yes.
the average, or because in VASP, I think the spin orbit coupling energy is associated to every atom, I think.
Yeah, you are talking about this situation, right?
Yeah.
Yeah, okay. So let me put it full screen. So in order to calculate the DMI, if I understood correctly your question, how we are getting this associated spin orbit energy, how we reveal it, correct?
Yeah, I mean, since there are like 4 different atoms and each have the energy change, so like how do you calculate the final coupling energy showed in the figure?
Yeah, well, actually, if you're asking more technically, I can show you again the previous slide of how we do the calculation itself. It is right here. So let me, yeah. So yeah, it is. The technique is right here. So there are 2 situations. Either you allow to enforce these clockwise and counterclockwise configurations of your all cobalts, okay? So you do these spin spirals in the 2 situations.
Mm-hmm.
But this will give you the total DMI.
Yeah.
And you'll see that the cancellation, actually, if you look at supplementary material, we explained in detail all the expressions, how we are getting into those. But if you look, so that is the situation of a total. How we do it here, well, you know that you can constrain the moments, right? So we were forcing the moments be collinear in these 2 layers, and we were allowing, and we were really, they are not easy to enforce, but it is like you have to iteration by iteration, you go with the constraint fields, and then you can imposing the constraint fields only in these 4 particular atoms, so that you force them to create these spirals. Eventually you will get rid of a penalty energy, and finally you will end up with this configuration. And this is exactly what is shown here. So we are getting then the value as a difference associated only with this cobalt, and then we look separately, well, at the same calculation, but separately in the spin orbit matrix, and we see where the spin orbit is actually distributed. And this is how showing with these blue bars. I don't know if I answered your question.
So actually my question was like, when you are calculating the spin orbit coupling energy in the adjacent, let's say the first platinum layer, right? And there are like 4 different platinum atoms in this layer.
Correct.
And in VASP, you have the spin orbit coupling energy for different atoms. So my question was like, when you are showing this graph, this spin orbit coupling energy is the average for this 4 atom or like any individual atom? I mean.
Oh, yeah. Oh, okay, now I see your question. Of course, it is per atom. When we are talking about the DMI microscopic constant, we are talking about per atom per bond.
Okay.
Of course, you have to divide and to take into account. And this is actually division by 12 is taking care of that.
Yeah, right. Yeah. So that is one of the thing. And another, like when you are talking about the VCMA coefficient, like for the VCMA coefficient,
For DMI or for PMA, sorry?
For PMA basically.
Yeah.
So we need to consider the relative permittivity of the insulator, right?
Yeah, I'm sorry, could you repeat?
So for the VCMA coefficient, we need to consider the relative permittivity of the insulator material, let's say MgO or other.
Correct, you're right, yes.
So, like what value you are using, the standard experimental value, or it is changing for like different structure to structure, like depending on the strain or other.
Yeah, I understood your question. It's a very good question. So why our approach was, if you look in our paper, our approach is, I didn't show it here, but in a figure 1 and 2 in a paper, you can see we calculate when you create this electric field across your structure, and then you really trace your averaged electrostatic potential, you will see that the gradient of this potential, which is giving you electric field, you can really visualize it across your structure. And our approach is, if you already have this drop, I mean, if you already directly, we calculated the VCMA by dividing by this electric field, which we're already getting from our calculation, which is normally taking it already into account. So you see, it is already there. So therefore, in our case, we didn't divide it by this dielectric constant. I know what we are talking about, that there are now some works appearing where we have, in addition, to divide. So I'm not convinced that we should do it, because we are looking at electric field already directly, which is a drop which is across a structure. So normally it is taken into account. So I don't know if I answered your question, but this is our approach here. Because we divide directly by calculated value of the electric field, what we see as a response, you see?
Yeah. So I have one more question. I'm sorry if I take much time. So the thing is, like for the magnetic anisotropy, the energy is basically, the magnetic anisotropy energy is basically the energy difference between the in-plane and out-of-plane spin configuration, right?
Yes, correct.
When you are showing the magnetic anisotropy from every different layer, I mean, how did you calculate this thing in like to get the layer result magnetic anisotropy? Like how do you configure the spin?
Yeah, how we're getting this layer result. Yeah, it's actually what you are looking for, and it is Ali did actually excellent work on this, on identifying, because it was not trivial to do it. At the same time, I remember colleagues also in the States, Dima Parkov and colleagues, they were looking at Samsung into this also. And it's actually, you can get, if you read, it is in the manual of, for example, of the DFT codes. Sometimes they don't put it in a manual, but if you analyze the codes and you see really what is getting there, there is actually more than usually is. And identified actually the spin orbit matrix elements. They are already, you can get them out and they are printed. Now the question is how from those energies you are constructing this. Of course, there were several tests. And finally, when we were sure that by taking, you have to look in the, actually this layer result is a result of, let me show you, where, for example, here, when you are getting these elements, you sum them up together, you will get, but of course you should take care of a double summation. Then you will get, if you are getting the total anisotropy, then it means that that's fine, it works. So you should be careful here, not for every system it will work. And then you should ask a question whether the pseudo potential is good, whether it is not good, etc. But in our cases, we're always making sure that the sum will be giving you. But the answer to your question directly is the following. You look the matrix elements, spin orbit matrix elements, which are giving you those from different orbitals hybridizations, and then by those at every atom, because they are resolved per atom, you can get actually built these layer resolved situations here.
Okay. Yeah. Okay.
Hope I answered your question.
Yeah. Thank you very much.
You're welcome.
Okay, thank you. Yili, please go ahead with your question.
Hi, thank you very much for a nice talk. So I have a question. For an experimentalist, do you have any suggestions for the 2D and the ferromagnetic interfacial coupling part? Do you have any suggestion for experimentalists how to get a nice interfacial coupling between 2D materials and ferromagnets? And in particular, can you comment on two types of defects for the interfacial coupling? One is the lattice mismatch, and the other is the roughness of the ferromagnets.
Yeah. Are you talking about the metallic ferromagnets, or you're talking about proximity part?
The proximity part.
Okay. So let me go to that part. So because the calculations are usually heavy, to answer about this first, we have, of course, to find a good matching in our calculations. We are probing different stackings, and obviously, when you relax the structure, you should relax to some stable configuration, and this is actually how we are doing it. But usually, when we test, for example, when we started for europium oxide, we tested several different possibilities, but you can immediately see that you have to use the lowest energy one, and we went with that one. So I don't know. I don't know how to about the suggestions. Actually, if you look now in recent works on this proximity-induced phenomena, now with a whole family of two-dimensional materials, you started to see this proximity-induced, and everything associated with the spin orbit, as I mentioned, is actually a very, very rich and exploding area now. And I mean, your question about which material I can suggest for stacking, I mean, in experimental works which I mentioned, actually, let me put them back here, is for example, I think that this one was europium sulfide graphene. Bart van Wees was using yttrium garnet graphene, and he did a nice Hanle measurements.
Okay.
Now, of course, I mean, there are some ideas also which materials to go. And for example, Leila Zanoli, she was talking about the DMO graphene interface. So I think that there are many studies existing. So it's hard for me to pick you up exactly which material you should look for. But I think that one of the most interesting materials now you should look to van der Waals materials interfaces, and everything which is happening there is actually very, very rich physics will be coming, and especially related to spin-orbitronics. So that is actually the area which is like very, very, I don't know if Aurélien Manchon, who was one of the speakers, was talking a little bit about that or not, but that is actually, hard for me to pick up one, because I'm afraid just to put you in the wrong direction. I just,
Okay, let me try to change the way of my question. So in these slides, you have a variety of different interfacial exchange splitting predicted between graphene and different materials, just the previous slides. And no, the slides that you show many different values. Yes, this slide. What is the biggest impact parameter for having the largest exchange splitting? Let's say lattice mismatch, or the material, the elemental selection.
For example, in case of europium oxide, it was very, I mean, it is a magnetic insulator, right? And you see that in one of the, if you look in the gaps of this, you can see that actually in one of the spin channels, there is these 4 F states which are sitting there.
Okay.
And I think that is actually playing quite a role in getting, let me show back this in this situation. So because you see europium termination, and you put on the top of it graphene, and then this hybridization, this will play a tremendous role, these 4 F states. So that is in the case of europium. Now, in case of yttrium garnet, frankly, it is very hard to tell, because it is, I mean, if we look at the band structures here, you see that how many different bands, well, of course we can identify them, and I think that we're trying to identify all those, and we can, but I think that, yes, we can, it requires additional work to do, but yes, we can dig it also and to find responsibles for getting this splitting here. But it is materials, and they are very, very complicated, as you see here. It's actually quite horrible. And then it requires, actually, we didn't get into really deep into that. But yeah, so I don't know if I answered your question, maybe not fully, but
okay.
yeah.
Okay, thanks a lot for your answer. Yeah.
Yeah.
Thank you. Wei Gan Wang, please. Next question.
Hi, Mairbek. Thank you very much for this very interesting talk.
Yeah,
I have a question about the first part, which is about the VCMA. So basically, I think the conclusion was that in a perfect interface, not over-oxidized, not under-oxidized, the VCMA effect was maximized. Is that correct understanding?
I think you're talking about this slide?
Yeah, I'm talking about this slide, yes.
Yeah. So the pure situation I already described, and here the message is very, as I said, in a pure situation, the second monolayer from interface is playing the crucial role. But if you look at the over-oxidized, the situation is changing, as you see. Now the first interface is actually playing the more role. And actually, if you look in our paper, we are talking about that. And then for oxygen-migrated case, actually we are getting almost nothing as a VCMA itself, but we're talking here again about charge-mediated thing, right? So there is no migration at all. So if you can precise your question, I don't know if I'm answering it or maybe.
Yeah, actually, by looking at this slide, I think it's almost similar in the pure case and the over-oxidized case, right? If we compare the total.
Yeah, they are similar. And we were getting always like, you see 15, 20. Well, therefore we think that that charge-mediated story cannot get you very large values. I'm not yet convinced yet, actually. Of course, there is this open question remaining about the dielectric constant. One of the previous colleagues asked in previous questions. As I said, for a moment, we are not convinced. We discussed with our experimental colleagues how this should be calculated, and for a moment, we are not convinced that you should really do that. But yes, the answer, the charge-mediated story, this is the value we are getting, and for over-oxidized case and for pure, they are comparable. Only the origin is different, but I mean the contribution of one or another. But for the values, as you see, they are similar.
Right, right. So I'm not sure you are aware of another study which was quite a few years ago. I think it was 2010 by Nakamura and A.J. Freeman. So,
yes, of course I'm aware, yeah.
Yeah, where in their study, they sort of suggest if you have iron oxide there, so it's like a severely over-oxidized, then the effect can be larger. I mean, why there is such a difference between your calculation and theirs?
First of all, I remember I was looking carefully into that paper, and if I remember correct, so it was several years ago. I mean, it's actually yeah, of course, we're looking at that paper. And my final conclusion was actually that I was not sure, I'm not sure if they were really looking at it exactly this way. When they were talking, I think that when they were suggesting this, they were indeed telling and comparing by looking at the band structure, these two situations, and I don't remember exactly the details, but somehow, of course, I looked into this paper carefully, but for some reason, I came to a conclusion that it was not exactly the same way we were looking at the thing. No, it's if you read carefully there. Michael, I don't know. I got convinced that we're talking about a little bit different things. So it's not the same way. Our approach is straightforward. We just really, they did it also. They approached a little bit differently. But in our case, I mean, we are always using the same approach, and we just directly now getting it this way. And our conclusion is this one, that they're comparable. Now for the I will maybe I should look again. Maybe you're right. I don't, but I remember that I looked carefully, and my conclusion was that no, we are not talking exactly about this same thing.
Okay, thank you very much. Yeah, I will look again as well. Yeah, I had the impression they have a somewhat different calculation, but you might be right. They might be talking about a separate issue. Yeah. Thank you.
But even the way of estimation was not. It was not this one. I mean, it was a different, as far as I remember.
Okay, thank you.
Okay, thanks. We have a question on Twitch. Let me try to reformulate it. So the question is about the DMI at the interface of ferromagnets and topological insulators or materials with the high spin Hall angle. So I guess what is known about the interfaces between topological insulators and ferromagnets like cobalt, and is there any relation between DMI and the spin Hall angle?
Okay, very interesting question. Of course, there is. I mean, there is a direct relation, as I said, between Rashba and DMI. That is actually, you can even derive from Rashba DMI. But regarding the topological insulators, obviously, this is a very important question, and there are several, I am aware that colleagues are looking into those, both experimentally and also theoretically, including us. For example, Hongxing with his group, we are looking into, we collaborate also on that. And we, of course, we put on the top of a topological insulator the different magnetic materials and trying to estimate the DMI in these interfaces. And well, we're getting some interesting things, and I know my experimental colleagues, they're also getting some good. But the answer is, of course, DMI is a spin orbit phenomenon. If it is a spin orbit, then obviously, if you have a topological insulator interfaced with as you remember, there was a nice work that topological insulator itself, it is a booster for spin orbit torques. It is a booster for lots of plenty of different. Because of spin to charge conversion, there is recently my colleagues. Maybe you've seen their very nice work also about the spin charge conversion, which they got in collaboration with the CNRS Thales colleagues. There is the very simple answer, yes, and different groups are looking into this, and of course there is a relation. So that is an answer. However, you have to be careful, of course. If you go, and it depends, obviously it depends which ferromagnet you will put on topological insulator. The nature of material obviously will play a huge role. For some of them, you will get very large values and significant boosts. For others, you will get very small. Actually, in some sense, it is similar. Even here, you can ask a question. Why for cobalt gold? Gold is also high spin orbit material. Why the DMI for cobalt gold is actually small, and for cobalt platinum is extremely large? I mean, it's tremendously large. Why is this happening? And the answer is, because both, you can tell, platinum and gold are strong spin orbit elements. What is important is, yes, the matching between the two. What happens is, one of the explanations what we gave was that if you look at the gold or platinum 5D states, which are important here, their position in respect to the Fermi level, which is defining whether it will create a large DMI or not. This was our explanation. What happens in the case of a gold, you already got it filled completely. And at the Fermi level, finally, you don't have any more much of those, which are really strong spin orbit contributors, 5D states. While in case of a platinum, you are in a situation where it is ideally placed when you match it with a cobalt, so that it provides you very nice, the feeling and position of a Fermi level is such that it will give you a very nice DMI. So obviously the same situation will happen with the topological insulator. Depending on the material that you will put on it, some of them you will get a very strong boost, and I'm sure that you will get much larger than for cobalt platinum. But in other situations, you will get not as large. I mean, that you should expect that. So the matching between the materials obviously is, so I don't know if I answered the question, but this is what I can tell you.
Okay, thank you. Are there any further questions in Zoom or Twitch? Let me ask you in the meantime about this device with graphene and 2 ferromagnetic gates that you had.
This one.
Yeah, the one before that, not the multiferroic. I mean, I have a more general question. Just 2 magnetic gates. Yeah. So what is the mechanism of this large magnetoresistance here? Can you explain that?
Oh, yeah, of course. So if you look at, for example, let's look at the yttrium garnet here, bands. I don't see, actually in our paper, we gave all the conductances resolved for all the contributions, and you can already see it. But we can already see it, what happens, for example, in case of ink. You see that we have this almost half metallic region. You put your Fermi level here, and you will have only majority band. While here, you will have only minority state band, okay? And now imagine you will be putting it, you will magnetize your graphene by putting it parallel or anti-parallel. Obviously, you will work, it will work again as a similar to a classical spin valve in some sense. So that is an explanation. You will have, if you trace the conductance as a function of, you do exactly for these energies and your conductance contributions, you will see, depending on your configuration, you will see immediately the 4 conductances what usually we're tracing, including you, Kirill, usually you do it also the same way. If you ask a question for parallel configuration, what is the contribution of a majority states and minority states? And then for anti-parallel contribution, what is the contribution of majority and minority? You will see that within this energy region, where we observe the huge magnetoresistance, some of them will not contribute at all. But for anti-parallel situation, it will be completely locked, closed, while for parallel it will be open. So it is a classical spin valve situation from that point of view.
But graphene is not gapped in that device, is it? So
I'm sorry?
The graphene is not gapped in this system, is it?
No. Well, I mean, it is not, but okay. If you look at the device, you putting the lead. Obviously, the position of your Fermi level is what we are talking about. Is you will need to bring by gating. Obviously, you see that if you look in respect to the 0 is a Fermi level of your chemical potential of your leads, and a graphene which is in the middle and also in the lead. But in this magnetized region, what is happening, you are getting it heavily doped, as you see here in this band structure, because you see minus 0.7, which is a heavily electron doped. The only one out of 4 which is doped with holes is a CF4. And now, therefore you see for CF4 the big peak. Well, I mean, it is not as big compared to others, but for EG, for example, you are getting it exactly at this energy region. And the idea here, it will be as if you of course, it is the conductance as a function of energy in respect to the Fermi level. You will need to, of course, think of a gating, because the problem of this doping should be solved. So I don't know if I answer your question, but yeah, the idea is here that. And one of the propositions was actually, we thought also about this idea. If you put on a graphene on one side EG, on another side CFO, because this is about plus 0.5 hole doped, and this is electron doped negative. Then we thought that we would compensate it in a way so that we bring it as close to as possible to the to the best situation. And in some sense, this idea is now realized for van der Waals 2D materials in a recent paper by Jaroslav Fabian in collaboration with Branislav Nikolic. You might see these papers. they did actually this idea when they were using two opposite dopings and for van der Waals situations, but they were still talking about this proximity story. They were talking about the spin torques, the spin accumulation induced, etc., spin orbit story. But the idea is, yes, I don't know, Kirill, if I'm answering you, but be careful that here we are having electron doping, and all the large magnetic resistance you will expect only within this region where you have a heavy spin splitting. Obviously, if you look now, what will be happening in upper there, the situation is different, and therefore in that region you are not getting a larger, well, you are having some noise and not larger magnetic resistances.
So you need basically to have the Dirac cone somehow tuned to the Fermi level.
Correct. Yeah.
Okay. Thank you. It looks like. Let's see. Do we have any more questions? So another question. Yeah, so do you know if there's a difference for the DMI for materials with negative and positive spin Hall angle? I guess the answer is generally no, but what do you think about this?
DMI for?
Is there a relation between DMI and the sign of the spin Hall angle in the normal metal?
Very interesting question. So the DMI, as I told, giving you example of a cobalt gold versus cobalt platinum, is defined obviously by position of your, for example, of your 5D states in respect to the Fermi level. You see that the chirality is changing the sign. Now, if you take a classical work by Fert and Levy, 2010, on a spin Hall effect, then you see that if you look at the spin Hall angles, we did actually with them also a couple of papers, and in collaboration with my experimental colleagues, Laurent Villa and colleagues. And if you look there, you can see that skew and side jump contributions, both they are different, of course, but you will see how when you are going within the row of a 5D elements from a left to right, your spin Hall angle will be changed from positive to negative. And I think the question is coming from this. And because that change was also related to the position, really so-called, we're using, in order to calculate spin Hall that time, we're using Friedel sum rules. And really the feeling and position in respect to the Fermi level of the impurity in respect to the host was defining the sign of the spin Hall angle. So from that point of view, obviously there is a similarity and it might be some correlation. However, I can answer already more affirmatively regarding the Rashba-induced DMI, which I gave you an example. And here, I'm almost certain that the Rashba sign and the character of Rashba splitting, it will give you, it will be definitive also for the DMI chirality. So there is the correlation. And if that, so from that point of view, there is a correlation between spin Hall and because in both cases, what you see, what you look is how you are feeling, how interesting, everything is how your 5D states and how they are positioned in when you created your system, whether they will be below or above. So, and I think that if they will be below or above, this will be defining your spin Hall signs. This will be defining your also, I gave you an example with the cobalt platinum versus cobalt gold. So yes, from that point of view, I think, yes, there is a correlation if we think that way.
Although if you think about the spin Hall angle in many materials, it's believed that the intrinsic mechanism dominates in there. It's presumably very curvature, so things like avoided crossings. So it's a bit more delicate than...
No, but I agree, of course, it is delicate. I was thinking to like more generally, because the question is whether they are correlated or they're related. I think that yes, in the end of the day it will be, but of course, but with the Berry curvature, etc., you can also it is related to. You can derive again. I mean, all the family of spin orbit phenomena. But of course, we have to distinguish between. You are right, between intrinsic and extrinsic. We have to distinguish. But if you take well, from that point of view, of course, when we talk about Rajba and we talk about the spin hole, from that perspective, if we talk about extrinsic induced spin hole, I agree with you, it will not be the same. If we talk about intrinsic one, not impurity induced, then which is a band structure more and Berry, etc., then in this case, of course, it is more delicate. I agree with you. Okay.
But also, I mean, generally speaking, Rajba has nothing to do with the spin hole angle in the normal method.
Of course. I mean, that I totally agree, because Rajba is not extrinsic anyhow. It is just a property of, I mean, you see local. Yeah, it is interfacial property because you have this interfacial field, which is, of course, the origin is different. I mean, I agree with you totally.
Okay. Alexei Kovalev, please go ahead with your question.
Yeah, so it's basically also related that if you are discussing then relation to spin hole angle, you then should say what the mechanism and if you have extrinsic mechanisms or not, and if you have disorder or not.
Yeah, I agree, Alexei. Of course, I agree with you.
Okay, yeah.
You see, I started from an extrinsic mechanism. And from extrinsic point of view, again, I was referring to this classical work by Ferton and Levy about extrinsic hole of a non-magnetic impurities in non-magnetic host, as you see.
But you don't have disorder in your calculation, right? So
of course. No, but the question was whether the spin hole in a metals, etc., the sign of it could be related to the DMI in this interface.
But how can it be related if, like, it can be extrinsic dominated, it can be intrinsic dominated, so...
Yeah.
In your calculation, you don't even consider
well,
disorder.
actually, we do have a disorder a little bit. Let me show you. We have ideal interfaces, except, of course, our colleagues, they were experimental colleagues, they are not happy with the ideal interfaces in the calculations that they were asking. So we were just simply swapping, and you can, well, in some sense, you cannot still call it that it is appropriate disorder calculation, obviously. But when you swap, you mix your cobalt and platinum in some places in your interface, and we calculated the DMI. And this is this point for cobalt platinum. When you start to swap a cobalt and platinum atoms at the interface, the impact is that you strongly reduce your DMI. You see? And that is.
You still don't know whether it's extrinsic or intrinsic.
That I agree, of course, with you.
Can you
but,
answer?
Well, in some sense, I mean, if you look at the Fert-Levy mechanism of a DMI, that is if you ask a question whether it is extrinsic or intrinsic, what you would tell? Because you see that you have like there is a heavy atom which is mediating interaction between two magnetic atoms. So whether for you it is can we see it like a impurity which is sitting next to two magnetic spins and mediating this interaction, or
no? But it's for sure matters for spin hole angle, right?
Right, but here it matters also for DMI, you see, right?
No, but spin hole angle will depend on whether it's intrinsic or extrinsic mechanism. So if you're trying to compare to spin hole angle, you have to know some information whether it's intrinsic or extrinsic mechanism. No,
of course, strictly speaking, you, Kirill, you are right. I mean, it's I went too far in making this analogy. But I mean, I was trying to answer the question, and the question I think which was in that sense, yeah. So.
Okay, thank you.
Okay, Yang Wang, please go ahead with your question.
Hi, Professor. Thank you for your nice talk. So when doing experiment, I found PMA at platinum cobalt bilayer, and without the special oxide like MgO. So I don't know whether do you know whether this is common? So whether it is easy to get PMA as platinum cobalt bilayer?
Your question whether for platinum cobalt bilayer without MgO we're getting PMA.
Yeah.
Of course there is a PMA. Yeah.
Okay.
Yeah. You know that even I can tell you more on that. How the PMA first observation at SpinTech in 2002 and 2003, 4, etc. When one of the first experiments they were doing, of course this was a spotted samples, etc. But platinum cobalt was known for PMA and they could see it. And then when they put on the top of it alumina first and oxidize it, eventually they put Mg, magnesium, and then they oxidize it. And then they see the anisotropy enhancement. And one of the questions was how you distinguish between whether the contributions are coming from an interface with the oxide versus interface with the platinum side of cobalt. And actually one of the works was of colleagues was actually to really show that whenever you oxidize, you clearly have on the top of a PMA what you already have, you have an additional PMA which is coming from a interface with the oxide. So this is how the logic was. So yeah, the answer is yes, of course you have a PMA for cobalt platinum. Yeah.
Oh, thank you.
Mm-hmm.